The encoding/JSON package can marshal any struct you give it. It doesn't know your types at compile time. It reads the field names, types, and tags at runtime and produces JSON accordingly. That's reflection. This episode covers the reflect package, the mechanism behind Go's serialization libraries, validators, ORMs, and testing utilities. You'll learn when it's the right tool and, just as importantly, when to reach for something better. Go is statically typed. Every variable's type is fixed at compile time. Normally, that's exactly what you want. But sometimes you're writing a function that must work with types it won't know about until it's called a JSON marshaller, a database mapper, a config loader. Reflection is Go's mechanism for inspecting and manipulating values whose types are unknown at compile time. The reflect package provides two fundamental types. Reflect. Type represents type information, the name, the kind, the fields of a struct. Reflect. Value represents a concrete value of some type. You can read it, and with a pointer you can modify it. You get them with reflect.typeOf and reflect.valueOf. Pass any value. Get back a type or a value that you can interrogate. The practical payoff, the standard library's encoding/JSON package uses reflection to iterate over your structs fields, read the JSON struct tags, and build JSON output, without knowing your struct's definition when JSON.go was compiled. Every time you call JSON, marshal reflection runs under the hood. Reflect.typeOf returns a reflect type. From it, you can ask questions. What's the type's name? What kind is it? If it's a struct, how many fields does it have? And what are their names and types? Kind and name are different things. Kind is the underlying category, struct, int, slice, map, ptr. Name is the declared identifier, person, user ID, int. A custom type user ID int has kind, equal to int and name, equal to user ID. When you're writing generic reflection code, you usually switch on kind. It tells you what operations are possible. Name tells you which specific type you're dealing with. For structs, number field gives the count and field. I returns a struct field with its name, type, and tag string. That tag string is how encoding/JSON finds JSON name and maps it to the right JSON key. Reflect.valueOf wraps the value. From the wrapper, you can call int, string, bool, or float to extract the concrete value, but only after checking that the kind matches. Calling int on a string value panics. The settability rule is the most important thing to understand about reflect. Value. When you pass a plain value to valueOf, you get a copy. You can read it but not modify the original. Canset returns false. To modify a value through reflection, you must pass a pointer. Then call .elem on the value to unwrap the pointer and get at the pointed to value. After that, canset returns true, and you can call setInt, setString, setBool, and so on. This mirrors Go's normal rules. You can't modify a value passed by value, but you can through a pointer. Reflection just makes the rule explicit with canset, instead of a compile error. When you're writing code that handles multiple unknown types, a switch on val. Kind is the reflection equivalent of a type switch. The difference is that kind groups types. Reflect.int matches int 8, int 16, int 32, and int 64. A single case handles the whole family. For numeric kinds, use val. Int. It returns int 64 regardless of the specific int type. For strings, val. String. For floats, val. Float. For booleans, val. Bool. For slices, val. Len. For structs, you can iterate fields with number field and field. This is the core pattern behind any reflection-based library. Read the kind. Branch on it. Extract or set the value using the appropriate method. Struct tags are Go's metadata system. A tag is a backtick string after the field type in a struct definition. Multiple key value pairs fit in one tag string. Reflect.struct tag. Get key extracts the value for a specific key. This is what encoding/JSON reads to map Go field names to JSON keys. Validate required is what validation libraries read to know which fields are mandatory. ORM libraries read DB column name to know what database column a field maps to. Reading tags at runtime is free from the framework's perspective. It doesn't change how your struct is compiled. The tags are purely metadata, but they do influence how your struct behaves when passed to any library that reads them. When writing your own reflection-based utility, struct tags let your callers configure behavior per field without changing code. They change the tag string and get different behavior. Field by name searches for a struct field by its name string and returns the corresponding reflect value. Before calling any method on it, check is valid. If the field doesn't exist, you get a 0 value and calling methods on it panics. Interface converts the field's reflect value back to a plain interface. From there, you can type assert to the concrete type you expect. This is the bridge between the reflection world and the normal Go world. The ability to access fields by name at runtime is what makes generic utilities like getField, name possible. The caller doesn't have to know the struct's type at compile time. They just pass the name as a string. Reflect value. Call invokes any function whose value you hold. You build a slice of reflect value for the arguments 1 per parameter and call returns a slice of reflect value for the results. This is how Go testing frameworks call your test functions, how dependency injection containers call constructors, and how some RPC implementations dispatch calls to handler functions. The function is identified by name or by type at runtime. Reflection dispatches it. The argument count and types must match exactly. Otherwise, you get a panic. Reflection doesn't give you any compile time protection here, which is part of why it's a tool to use carefully. Reflection is appropriate when the types are genuinely unknown at compile time and the behavior is driven by runtime information. Struct tags, type names, interface implementations, serialization libraries, ORMs, validators, config loaders. These are the canonical use cases. Reflection is inappropriate when the types are known. Just use those types. It's inappropriate when the algorithm is the same across types. Use generics. It's inappropriate when behavior varies by type. Use interfaces. And it's always inappropriate on hot paths, because it's 10 to 100 times slower than direct operations. The rule of thumb: if you can express what you need with generics, do. If you need runtime dispatch and the typeset is open-ended, use interfaces. Only reach for reflection when neither of those works, when you genuinely need to inspect the structure of an arbitrary type at runtime. A good check: if you're writing an internal function used in one place, and both the caller and callee know the types, there's no reason for reflection. If you're writing a library function that accepts interface or any and must work correctly for types the library has never seen, reflection may be the right tool. Field access through reflection is 50 to 100 nanoseconds per operation. Direct field access is about 1 nanosecond. Function calls through reflect value call are 100 to 200 nanoseconds. Direct calls are 1 to 2 nanoseconds. For most code, this doesn't matter. The reflection happens once at startup or once per request. For code on a hot path inside a tight loop on every item in a large batch, the overhead matters. The main optimization when you can't avoid reflection in a loop: cache the reflect type outside the loop. Reflect.type of itself has overhead. If you're calling it for the same type on every iteration, you're paying that cost repeatedly. Assign it to a package-level variable once and reuse it. The other option for true performance requirements: code generation. Tools like EasyGen and Go Generate produce type-specific serialization code. It's faster than reflection because the compiler can see and optimize the concrete types, but it requires a build step and generated files to maintain. Reflection lets you inspect types and values at runtime. Typeof gives you reflect type, name, kind, struct fields, tags. Value of gives you reflect. Value read with int, string, bool. Write through a pointer with elem then setInt etc. Switch on kind for type dispatch. Read struct tags with tag. Get. Call functions with value. Call. Use it when types are genuinely unknown. Prefer generics and interfaces when they fit. Cache reflect. Type to reduce overhead in loops. Next episode, profiling, performance, and memory management, how to find and fix bottlenecks in real Go programs. This course is based on the complete guide to Go programming, available on Apple Books and Amazon. Find it at pixelstech.net/book. See you in episode 23.